Principles of Bioproduct Separation, Module 11, Ultrafiltration and Electrophoresis, Segment 4, with me Yusuf from School of Life Sciences and Technology, Institute Teknologi Bandung. We have previously discussed about basic ideas, ultrafiltration and electrophoresis. In this segment, we'll discuss about electrodialysis and isoelectric focusing. Electrodialysis is largely used for dissolving protein solutions. Electrodialysis is most commonly coupled with precipitation, where large quantities of salts are added to protein mixtures to precipitate some of the proteins. Later, the salt and remaining soluble proteins must be separated, often by electrodialysis. The basic apparatus for electrodialysis is shown in the right figure. The simplest form is as shown at the top of the figure. The apparatus consists of three compartments separated by two ion exchange membranes, shown schematically as the dashed lines. The left-hand membrane permits cation exchange, for it is permeable to cations but not to anions. The right-hand membrane allows anion exchange, passing anions but not cations. The large protein cannot pass through the membrane. A solution containing the protein and a small electrolyte like sodium chloride flows into the center of the compartment. Sodium ions in the solution are drawn toward the cathode on the left. At this cathode, water is split to produce sodium hydroxide. Simultaneously, chloride ions are drawn through the anion exchange membranes toward the anode on the right. At this anode, the hydrochloride reacts to produce hydrogen chloride and an electron. Thus, electrodialysis moves the salt out of the feed solution, leaving a purified protein solution. In actual practice, electrodialysis uses a stack of membranes as shown in the bottom figure. In this stack, the protein solution is fed into one set of the compartments, and pure water is fed into an alternating set. The compartments are again bounded by cation and anion exchange membranes. Most of the salt exists as sodium chloride solution and does not react to form sodium hydroxide or hydrogen chloride. This lack of chemical reaction reduces the current required to remove the salt and hence makes the process much cheaper to operate. Isoelectric focusing is used to separate proteins with different isoelectric points. Isoelectric focusing can be directly applied to large-scale protein purification. Separation mechanism can be illustrated by considering three proteins, thyroglobin, hemoglobin, and myoglobin as shown in the right figure. The proteins have different isoelectric points. Let's consider hemoglobin as an example. Below a pH of 6.8, it is positively charged. At pH 6.8, it has no net charge. Above pH 6.8, it is negatively charged. The apparatus consists of three compartments separated by two non-ionic membranes. Feed solution buffered at a pH of 6.8 enters the central compartment. A protein like myoglobin is positively charged at this pH. As a result, it is drawn to the left towards the cathode. In the same way, thyroglobin moves toward the anode but stops as it enters the right-hand anode compartment. Hemoglobin is fed as an uncharged species and so will not be drawn out of the central compartment in either direction. For better visualization about ultrafiltration, electrophoresis, and electrodialysis, you may want to check these videos in YouTube. Until then, I am Yusuf from Institute Teknologi Bandung.